Hi, Calc students. Welcome to our lesson on section 7.7. I know super randomly is stuck here in chapter 5, but I think you will not mind so much because it's actually fairly straightforward. This is our lesson on what's called the L'Hopital's rule. And the L'Hopital's rule actually is going back to this idea of evaluating a limit. So really, it kind of belongs more with chapter 1. The reason why we can't do it in chapter 1 is because it also requires knowledge of derivatives. So it would be something that would fit maybe more after chapter 2, except that chapter 2 is already so long and crazy that I just choose to wait till now. But anyways, this is a method for evaluating limits, specifically limits that you get, or limits where you get what's called the indeterminate form after you plug in x. And also it usually starts off, I should say, as like a function or a fraction, where you have like one function dividing by another one, and then you plug c into both of them, and when you do that, you get 0 over 0. Or any one of these, infinity over infinity, or any kind of variation of infinity over infinity, basically. These are all considered indeterminate forms, and L'Hopital's rule applies to all of them. Again, this is what you would get if you just initially substituted c into these equations. On a side note, because in Calc AB we only cover this particular type of indeterminate form and how L'Hopital's rule works for that, there's actually more application of it when you have indeterminate forms of this nature, like 0 times infinity, 1 to the infinity, 0 to the 0, infinity to the 0, infinity minus infinity. So these scenarios also can be rewritten to be compatible with L'Hopital's rule, but we, for this class, are focusing mostly on these forms. Those of you going on to Calc BC or other calculus classes in college may also need to know how to handle these scenarios. So just wanted you to know that there are other scenarios out there. This lesson, however, will focus on the ones highlighted in yellow. Okay, so what does it say? It's basically saying, suppose you want to take the limit as x approaches a constant of this fraction of functions, and when you plug in c, you get 0 over 0 or infinity over infinity. What you could do is get a new fraction. The new fraction would be made up of the derivative of the top, separate, and then the derivative of the bottom, separate. So this is not the quotient rule, okay? So just be aware of that. We're not taking the derivative of the whole fraction. We are just changing the expression. So this expression is different from that one, but they will have the same limit. That's what L'Hopital's rule realized, is that the limit of this expression for x going to c would be the same as the limit of that expression for x going to c, and this a lot of times will help get rid of that indeterminate form problem. So let's take a look at example 1. You may recall these. I used to like assigning a bunch of these because this limit is actually finding a derivative itself. And so you used to have to recognize, oh, okay, this is f of x plus h, and then minus f of x all over h. H is approaching 0. This is a derivative. This limit is equal to f prime of x. And then you would have to go, well, then what's f of x? Oh, it's tangent. What's the derivative of that? Secant squared, which is how I had you do this back in chapter 2, which still works. All of this stuff from chapters 1 and 2 still work. But another option would be, so notice here that the limit is h. H is approaching 0. So that means h is the variable, and we can treat x like a constant, because the limit doesn't have x going anywhere. X is staying right where it is. It's only the h that's going to 0. So L'Hopital's rule says, well, you could take the derivative of the top. So the derivative of the top would be secant squared of the inside, which is x plus h, times the derivative of the inside, which would just be 1, since it would just be the derivative of h with respect to h. And then minus 0, because I'm treating x like a constant, so the tangent of x would also be a constant. So this would be the derivative of the top. And then if I took the derivative of the bottom, which is just h, derivative of h with respect to h is just 1. L'Hopital's rule says, well, you can take the limit of this new expression. It's a new expression. This is not equivalent to that. This is not even the derivative of that, because I did the derivative of the top separate divided by the derivative of the bottom separate. That's not the quotient rule, so I'm not doing the derivative of the whole thing. I'm just getting a new expression, derivative of the top separately, derivative of the bottom separately, but the limit of that new expression would equal the limit of this expression. So usually, once you have found those derivatives, you can then go ahead and just find that limit by substitution. And so this would just equal secant squared of x, which we also know to be true based on the fact that this is a derivative of tangent, and the derivative of tangent is secant squared. So we know that this is the value for this limit. This is just showing you how you could also arrive there using L'Hopital's rule. So moving on to example 2, you might remember this one. This was our special trig limit back from chapter 1. We found the value of this limit by looking at the graph of sine of x divided by x, and we could see that this quantity was approaching 1 graphically. So we know the answer to this is going to be 1. But I want to show you again how we could utilize L'Hopital's rule to also arrive at that same answer. So L'Hopital's rule says you look at the top function separately and you take its derivative. Derivative of sine is cosine. You look at the bottom of the fraction and take its derivative separately. Derivative of x is 1. Then you take the limit as x approaches 0 of that new expression. This is my f prime divided by my g prime. Again, if sine of x is f of x and just x is g of x, using this setup here for L'Hopital's rule. So I find a new expression, take the limit of that expression as x approaches, whatever c was, which in this case is 0. So then I can just find this limit by substitution. Cosine of 0 is equal to 1. And so that's the other way that we could evaluate this special limit of sine x over x as x goes to 0. According to L'Hopital's rule, that limit would equal 1. Having seen the graph of this function, we know that that is true. So L'Hopital's rule works. Okay, so moving on to example 3, you may notice now our x is approaching infinity, but actually L'Hopital's rule can work in that scenario too. Not always, but if you get one of the indeterminate forms by substitution, it can work. So I noticed that if I were to plug infinity into my x terms, all of them, right, like quote, quote, substitute infinity, I'd have ln of infinity over infinity, which is still infinity over infinity, essentially, right? It's still a value that's going to grow indefinitely divided by another value that's going to grow indefinitely. So this is one of the indeterminate forms that can work with L'Hopital's rule. So I will try to find this limit using L'Hopital's rule. So I would need to take the derivative of the top by itself, right? So you're not doing quotient rule, you're kind of ignoring that for now and just doing the derivative of the top. So that would be the derivative of the natural log, which would be 1 divided by everything inside of it. So e to the 5x plus 3x. So it's 1 over the blop, the stuff inside. Then you multiply by the derivative of the stuff inside. So the derivative of e to the 5x, that also requires a chain rule. So it's e to the 5x times 5. And then just plus 3, which is the derivative of 3x. So this right here is just the derivative of the top. Now I will pay attention to the bottom and go ahead and take the derivative of the bottom. And the derivative of x with respect to x is just 1. So there really is no bottom or whatever. It's just gone to 1. So let me rewrite this expression. So I have 5 times e to the 5x plus 3 over e to the 5x plus 3x. So according to L'Hopital's rule, I should be able to take the limit of this and it would equal the limit of the original function, even though these expressions are not the same. But since this is basically the derivative of the numerator divided by the derivative of the denominator, it should, according to L'Hopital's rule, share the same limit. So now I will attempt to take the limit as x approaches infinity of this expression. So again, you might notice that if I plug in infinity for all the x's, I still end up with like a infinitely growing value divided by another infinitely growing value. So I'm not able to find the limit by substitution yet. However, it does qualify also for another L'Hopital's rule. So that's the other thing about L'Hopital's rule is you can continue to use it as long as you're getting indeterminate forms by substitution. Okay, so I'm going to use L'Hopital's rule again, but I'm going to also pause for a second to remind you of how we used to do stuff like this back in chapter 1. Back in chapter 1, when we had x approaching infinity, we would consider if it was one of 3 cases. We often referred to them as like big over small, small over big, or same over same. Because all of these are still, they still work. All of these are still in effect. This is just another tool to add to our list of tools. But as a quick reminder, when you had x approaching infinity and you ended up getting something that was bigger on the top compared to the bottom, this would either go off to positive or negative infinity. It would have no like finite limit. If the numerator had a smaller value than the bottom did as x got infinitely large, this limit would approach 0. And then if the top was similar in size to the bottom, it would approach like a fraction where you were dividing by the leading coefficients. Just a quick review there of chapter 1, how we used to do this, because I want to show you if you use that method, you might be able to recognize that these are the same size divided by the same size for the most part. It's e to the same multiple of x, e to the 5x, e to the 5x. But you have a 5 times this one on the top and then just a 1 times that expression on the bottom. 3 when compared to e to the 5x is like, it doesn't have any effect on this as x gets really large. It becomes irrelevant for large x's, and then same with the 3x down here. So we kind of ignore those for x approaching infinity, and we notice like these terms would be the ones that have the more effect. So they are the same size. You would divide the leading coefficients. You can tell from chapter 1 methods that this limit is going to equal 5. But I'm going to back up off of that for right now because I erased everything. Because I want to show you how it would work using the L'Hopital's rule. So we've got e right there. This is a fraction. All right. So the L'Hopital's rule would say, go ahead and plug in your infinity. Recognize that both the top and the bottom are getting infinitely large. Use the rule again. Take the derivative of the top. So the derivative of this part would just become 5 times 5 e to the 5x. And then that just goes to 0. That's the derivative of the top. And then the derivative of this part would become 5 e to the 5x. The 5 is here because of the chain rule. That's why the 5 was there as well. And then plus 3. So that's the derivative of the bottom. So according to L'Hopital's rule, I should be able to take the limit of this new expression as x approaches infinity. And whatever that is should equal the limit of this original expression here. Okay, so this just becomes 25 e to the 5x, and then I have 5 e to the 5x plus 3. So I still end up, when I plug infinity into all the x's, I still end up with infinity over infinity. It's not giving me a limit yet. So I can use the L'Hopital's rule one more time, or as many times as needed, as long as I keep getting either 0 over 0 or infinity over infinity. When I substitute, then I can keep using the L'Hopital's rule. Let's scoot this off to the side. Okay, so I'm going to go ahead and do this one more time. I'm going to take the derivative of the top. So this expression, by the way, is simplified. I'm going to take that out so that it's not in my way. This expression simplified to the limit as x approaches infinity of 25 e to the 5x over 5 e to the 5x plus 3, and it still was approaching an infinitely growing value in the numerator and then an infinitely growing value in the denominator. So no limit yet, right? Indeterminate form. Although if you're looking at the fact that it's same size, right, over same size, and 25 divided by 5 is 5, just, chapter 1 strategy is still good. But anyways, we're going to keep going. So now I'm going to take the derivative of this new numerator. So that would become 25 times 5 e to the 5x all over, and then this would be 5 times 5 e to the 5x plus 0, because now I'm taking the derivative of 3. Okay, so now we're getting somewhere. So now I have 125 times e to the 5x divided by 25 times e to the 5x, and no other terms, because as I kept taking the derivative, the 3x went to 3, and then eventually 3 went to 0. So now I can cancel out. I can get rid of those e to the 5x's, and that means this limit, as x approaches infinity, is approaching 125 divided by 25, which equals 5. So we would eventually arrive at that limit of 5, but this is just showing how you would use L'Hopital's rule to eventually get there. So these things from chapter 1 still work. But notice on the beginning, it would have been really hard. Like these things would have been really hard to tell. In fact, it almost looks like small over big because it's got the ln. It's because it's ln of e that it ends up being same over same. So L'Hopital's rule was really helpful right here to get us to this part. From here, you can either continue using L'Hopital's rule or recognize from here that it's now a same over same, and you could have gotten the 5 over 1 from this step. Either way. All right, so here in example 4, I have a situation where my x is approaching 0. So I would want to plug in 0 for each x and just see what I get. I notice that I get e to the 0 minus 1 over 0, and then that's 1 minus 1 over 0. So because I end up getting an indeterminate form when I substitute, I can therefore use L'Hopital's rule, or attempt to use L'Hopital's rule to evaluate this limit. So I would take the derivative of the numerator. So the derivative of that would be 2 times e to the 2x minus 0. Divide that by the derivative of the denominator, which is 1. So this just turns into 2 times e to the 2x. So this is what I get when I take the derivative of the top separately, divide it by the derivative of the bottom separately. L'Hopital's rule says that the limits of those expressions should be the same. Even though the expressions themselves are different, their limits as x approaches 0 should be the same. So I can evaluate this limit in order to evaluate the original one I was being asked to find. So this would just equal 2 times e to the 0, which is 2 times 1, which is 2. So the value of this limit is also 2. And you can always graph these functions to verify, is the y value getting closer to 2 on this graph as x approaches 0? And it is. And so therefore it would be confirmation that your process of solving was correct. Okay, so for our last example, we have one that's not written as a fraction, but sometimes you have to just sort of rewrite whatever expression you are given to make it match the structure for L'Hopital's rule. So for this one, I'm going to recognize that if I have e to a negative power, that would mean that that expression would end up in my denominator. So I'll have my square root in the numerator and then e to the x in the denominator. So I'm taking the limit of that expression. Now, again, if you think back to our chapter 1 scenarios, whenever x is approaching infinity, we could consider which of the 3 cases. This is a small over big, so this limit is eventually going to go to 0. So in this example, referring to those chapter 1 strategies, I think is easier. However, you can still use L'Hopital's rule, and so it's good to know multiple ways of getting the same answer. Okay, so L'Hopital's rule says, go ahead and plug in infinity to both your x's and see what happens. Both of these are getting infinitely large as x gets infinitely large. So this is an indeterminate form that works with L'Hopital's rule. So you would then have to take the derivative of the top. So the derivative of the square root of x, we'll think of that as x to the 1/2, would be 1/2 x to the negative 1/2. So that's the derivative of the top. Derivative of the bottom is just itself, e to the x. And this was on the top, this on the bottom. So here's our new fraction, and I'm just going to simplify that a little bit. So it's 1 over 2 rad x. All of that is over e to the x. And if you simplify that, you get 1 over 2 times rad x times e to the x. So now, when you're taking the limit of this as x approaches infinity, you now have 1 over all of this stuff. So when you plug the infinity in for the x's, you don't get indeterminate form anymore. You have a 1 on the top and then an infinity on the bottom. And so we have to remember what that means. If you have a fixed value over a growing value in size, that is eventually going to become 0 because it's going to be 1 over a bigger and bigger and bigger value every time, which is giving you a number that's smaller and smaller and smaller and smaller. So 1 over infinity approaches 0, so that's our limit. So even after just one round of L'Hopital's rule, it becomes very obvious that the denominator of this function is growing so much faster than the numerator that eventually the value of this equation here gets smaller and smaller and goes to 0 as x approaches larger and larger values, approaching infinity. And again, for confirmation, you can always enter this into your graph, like graph that on your calculator or Desmos and just see, is the graph flattening out toward y equals 0 on the right-hand side to get your confirmation. But that basically is L'Hopital's rule. It's very straightforward, and it's again for evaluating limits. So now I'm going to have you work on some practice problems from your textbook, and hopefully you can get it all done before you go home, have no homework on the weekend, and everybody wins. And then I'll be here Monday for questions.